Hello everybody, my name is Stoffel. I'm a mechanical engineering student at San Francisco State University, and today we'll be talking about the principles of tensegrity. To start us off, what exactly is tensegrity? Well, tensegrity itself is a term used to describe the characteristic properties of a three-dimensional object that is made up of at least two non-contiguous members acting in compression, supported by a series of contiguous linkages acting under tension. The term tensegrity is actually a portmanteau of the words tensile and integrity. While the concept of modern-day tensegrity began around the 1920s, with the name being coined sometime around 1950, examples of the structure date back to early skin-framed kayaks and Japanese paper shoji. Tensegrity structures come in all shapes and sizes and can be made out of a wide variety of materials. For example, large tensegrity objects such as this are used to form art, demonstrating an air of delicate balance, and these can be scaled up or down depending on the space allowed. Other tensegrity objects such as this one can act as a table or even a chair. The difficulty in creating a tensegrity structure for this purpose, however, lies in the stability and strength of the members in tension. The more weight you place on the top surface, the more unstable the balance becomes, and at a critical point, the entire structure can twist and collapse under the weight. More practical applications for tensegrity structures have been found both in the aerospace and biomedical fields. In this example, we can see how NASA has experimented with the principles of tensegrity with a rover that moves around on an uneven surface by altering the lengths of the compressive rods as well as the levels of tension in the supporting cables. Here, we can see how a complex tensegrity network can be used to mimic the range of motion of a human spine. This aspect can actually be expanded upon further to create tentacle-like robot manipulators with a wide range of motion. For my project, however, I opted for a table design, as I wanted a surface with which to display small personal projects across my apartment. For my compressive members, I chose to 3D print these parts in order to simplify the assembly and the repeatability of the project, on the off chance that any parts were damaged during the assembly. For the linkages in tension, I chose to rely on a nylon fishing line. There's no special reason for that, I just happen to have some on hand. However, I would recommend against anyone else using the same nylon line, as it made securing the platforms together increasingly difficult due to their low coefficient of friction. As you can see, while the top and bottom surfaces of the platform are circular, the outer tension lines are arranged equidistant from the center at a 90-degree interval around the center of the platform, forming a diamond or a square shape. In the center, there's a central string that holds the two objects together. This is essential for this model of a tensegrity structure. Due to the shape of the two solid linkages in the center string holds both platforms in a counterintuitive way. In principle, it makes it so that the bottom platform is actually holding the upper platform in the air through that center string, and the four strings on the outside of the object simply hold the orientation of the top platform into an upright position. If the top platform tries to lean in any direction, the opposite guideline will pull in tension, holding it straight up.